Now we'll study complexity class NP, and the definition will be using non-deterministic Turing machine. So once again, before formally defining what is a non-deterministic algorithm using non-deterministic Turing machine, we'll use snakes and ladders game to get a non-technical and intuitive example. Once again, we'll consider the snakes and ladders game, and this time we'll see how a non-deterministic algorithm works. So before going into technical definition using a non-deterministic Turing machine, we will see a non-technical and intuitive example of a non-deterministic algorithms. So the name non-deterministic algorithm means we do not know what will be the next step. So we have choice. So first, once again, we'll use this dice, and as we know that this dice has 6 possible numbers, 1 up to 6. So first thing is we should have a choice from 1 to 6. This is the first thing. And second thing is we have a bias. Now what type of bias? So first I will define the rules of the game. So this is slightly different from the usual game. So we have these numbers, we have some normal numbers, some numbers with ladder. So as before, we pick up the ladder and move up. And we also have snakes, snake bites, and we move at the tail. So the only different rule that we follow is that once a snake bites, we have lost the game. So snake bite means we have lost the game. So this is one change. And further, beyond 100, we assume that all numbers are snakes. So for example, if we are at 98 and our dice shows 3, so it will move to 101 and snake will bite and we have lost the game. So these new sets of rules will follow. And now what type of bias? So the bias is very simple. So first we'll define the behavior of a non-deterministic Turing machine, how it works. So it is based on, the move is based on the choice. So we have a function like this. F, its domain is the numbers 1, 2, 3, 4, 5 and 6, and range is also 1, 2, 3, 4, 5 and 6. So to the simplest possible function f from 1, so f is actually a permutation. So this is the number shown on the dice and this is the move that we follow. So the simplest possible permutation we can have is the identity permutation, fx equal to x. This is a permutation. And another example we can take is take this, call this f1 and call f2. f2x is equal to 7 minus x. So 7 minus x, we find its range as x ranges from 1 to 6. For 1 it takes value 6 and up to 6, so it takes up to 1, 6 up to 1. So these are two examples. We'll follow this simplest example. Now to explain the difference, how the behavior of the non-deterministic algorithm. So we have two things. First is choice and second is bias. So choice, we know, we throw the dice and we have a number from 1 to 6. Now bias, how we'll explain this bias. So bias is towards winning. Bias towards winning. So to describe this bias towards winning, first I will tell a story from Mahabharata. So you must be knowing the story of Mahabharata. Once there was a betting game of throwing dice between Kauravas and Pandavas. At the side of the Kauravas was Shakuni. So Shakuni cheated in the game. How he cheated? So his dice was not ordinary dice. It was a magical dice. So whenever he throws the dice, it always shows the number through which Kauravas can win. So this way Shakuni cheated and Kauravas won the game and Pandavas lost everything, and the result was ultimately the great war of Mahabharata. So this is just using the story to explain what we mean by bias. So here also we assume that our dice is a magical dice, means whenever we throw, so the function that we are using, this function f, so its output will never be a snake bite. So never a snake bite. This is magical dice. So this is our assumption. So and also we have physical realization of deterministic algorithms. We can implement them using physics, but there is no physical realization of non-deterministic algorithms, because in nature we can simulate this choice by physical process, like throwing a dice. This is a physical process, but in nature we cannot implement this bias. There is nothing in physics that has a bias towards winning. So this is the reason we do not have working non-deterministic machines, but we have working deterministic machines. And later we'll see we also have deterministic randomized machines, where the choice we can simulate using physics. So physical processes are randomized. So now I will give a sample of for both the two functions f1 and f2 how this bias works. Take a very simple example. Suppose we are at nearby some snake. This snake has number 30, 29, 30. So assume that we are this is also a snake, has number 26. So we can say, let's say we are at number 24 and we throw our dice. So now there are 6 possible numbers. 6 possibilities we can have are 1, 2, 3, 4, 5, 6. So here just first I am showing this bias for f1. f1 is the identity function, means f1x equal to x. So if the number shown on the dice is x, we should jump x. So here we can easily see that out of the 6 possible combinations, the numbers 2 and 6 we have a snake bite and we'll lose the game. So for example here it is shown 6, so 6 is forbidden. So the magical dice, actually I cannot simulate the magical dice. So the two numbers 6 and 2 will never come. So only possible numbers that will come for the case of f1 is 1, 3, 4 and 5. 2 and 6 will never come. Now same example for, suppose our so this is algorithm A1, non-deterministic algorithm A1, implementing the function f1. Better we call implementing the permutation f1. Now second example, suppose we have algorithm A2 which implements permutation f2. So once again possible choice when we throw the dice are 1 up to 6, but here the function is different. So 7 minus x, so this value 7 minus x, it should not be equal to the 2 snake bites. The value is 2 and 6, so value is 2 and 6. So the number x, means the number x shown on the dice, it should not be 7 minus the 2 numbers. So 7 minus 2 is 5, 7 minus 6 is 1. So our dice will never show 1 or 5, because for 1, if it is 1, 7 minus 1 is 6, snake will bite. If it is 5, 7 minus 5 is 2, again snake will bite. So this is the character of a non-deterministic algorithm. We have a choice, we throw the dice, and depending upon the number on the dice we make our move, and the dice is biased, means it may never happen that the move that will take is a losing move. So it will always make a winning move where there is a possibility of winning. So here by winning we mean arriving at the node 100. So here we can easily see that why the algorithm is called a non-deterministic algorithm, because we cannot predict the next move. And so if we run the same algorithm twice, we will see different behavior each time. And so we'll run the algorithm twice and see that we get different behavior. And also one more thing, that outcome is identical. So if we run the algorithm multiple times, we'll always reach, ultimately we'll reach 100. But the set of numbers that we travel will be different. So this we'll see by running the algorithm twice. So for our example, we'll use this simple identity permutation just for simplicity. We can also take any other algorithm, but the behavior will be identical. So simplest example we'll take, just throw a dice and jump the corresponding move. So next we'll play this game twice using non-deterministic algorithm, where we use the identity permutation. We run it twice and see that we get different set of moves each time, but ultimately we'll reach 100. So here also this once again I will clarify that actually this is natural dice and this is not a magical dice. So how I will simulate, if I will throw the dice, if it results in snake bite, so I will just flip it just to simulate the magic. So we start with 1 and play the game. So first we have 1, so I will also write the number. We write here 1, first move 1. So 2, jump the ladder, go to 55. Next we have 3, so we move at 58, write the number 58. Next 5, 1 2 3 4 5, 63. Two, so 65. Next we have 1, so 66. Next move again 1, 67. Again next move 4, 71. Again 1, 72. Three. So here we can see 3 is a snake bite. So because this is a magical dice, 3 will never come. So I'm just flipping to simulate the magic. 5. 72, we arrive at 77. 77. 1, we arrive at 78. 3, 81. 4, 85. Again 4. So here again we can see 89 is a snake. So I will simulate the magic. For magical dice will never show 4, it will show some other number, like here 6. So we arrive at 91. 4, we arrive at 95. 3, 98. 2, so now we win 100. So these are the set of moves. We have reached our goal, we have won the game. Now once again I will repeat and see that second times the number sequence will be different. 4, so 1 to 5 I will write and also compare. So one initial number will always be same, 1. Next we have 5, so we can compare the numbers. So these are different numbers, they do not match. Same way we continue and we'll see different sequence of numbers. 4, 9, again not matching with the corresponding number. 2, 11, so now we'll always get a mismatch. 4, 15, 4, 19. 3, 22. 5, 27. So all numbers we can easily see they are not matching. We have a completely different sequence, but ultimate objective will be same, the result will be same. So 2 we move at 29. Again different numbers. This time we are very slow, we do not get any ladder. 2, so we got a ladder. 31 move up to 67. So all numbers are different. 1, 68, we are getting different numbers. 4, 72, all numbers are different. 1, 73. 6, 73, so 79. Here we have matched. Here 79. 79, so this will not match. Every number is not matching. Again 6, so 79 we get at 85. Again no match. 2, so 87, no match. 1, 88. So now we are getting completely different set of values. 4, 92. 3, 95. 5, and we win. So now we can easily see that we are getting different set of numbers, number of steps are also different, but the ultimate result is same. In both cases we have won the game.